minus 2, that's minus 16, right? Y turns out to be minus 16. So what are the coordinates then? The coordinates of that point that we were looking for, they are ln of 4 over 3 and minus 16. These are the coordinates of that point. Did they call that point something? No. This is the point that we were looking for. All right, let's move on now. Last part of this, it says use this substitution, u equals e raised to pi x in partial fractions to find the exact value of this function. Now, okay, that's a 9-mark question. That's going to take some time. Okay, f of x, that was this original function. All right, so this is e raised to power 2x, 2 e raised to power 2x divided by e raised to power 2x minus 3 e raised to power x plus 2. Okay, so what we want to do is we want to use the substitution to find the exact value of this. Integrate this with respect to x. First of all, use that substitution. So they're saying u equals e power x. What's du over dx? That's e raised to power x. Make dx the subject. That gives you dx equals du over e power x. Input this in the question. Input this in the integral. U equals e raised to power x. So you would get 2u divided by e raised to power 2x. What's that? That's u squared minus 3u plus 2. What about this? Dx, you replace this with du over e raised to power x. Now we still have an x here. How do we eliminate that? We can again put that equal to u. So this gives us 2u over u squared minus 3u plus 2 whole times u du. U and u get cancelled and we have this fraction left. Okay, so we have to integrate 2 over u squared minus 3u plus 2 with respect to u. Now we can change the limits as well. Limits are values of x there. We can write down the limits. What's the upper limit and what's the lower limit? The upper limit is x equals ln of 5. The lower limit is x equals ln of 3. If u is equal to ln of if u is equal to e raised to power x, then what does this become? U equals e raised to power ln 5. That will give you u equal to 5. U equals e raised to power ln of 3. That's going to give you u equals 3 because ln and e are inverse of each other. We get these limits. Lower limit is 3 and the upper limit is 5. That's actually an easier 9-mark question. It's not that difficult as such. We had 2u squared here as well. That's what doing it in a hurry does to you. This is 2u in the numerator, so only one power gets cancelled here. And that gives you 2u over this. Now, it's an easy 9-mark question actually. All you have to do is just integrate this now using partial fractions, input the limits, and you get your result. Okay. All right, let's input, let's find the partial fractions. For this, 2u over u squared minus 3u plus 2. What are the partial fractions? We first will have to factorize this because denominator is not factorized. You can't find partial fractions unless it's factorized first. Can you factorize this? The numerator can be written as u squared minus 2u minus u plus 2. And then that can be written as 2u over u minus 2 into u minus 1. These are two factors that we get. Now, let's find partial fractions. Let's find partial fractions for this. 2u over minus 2 into u minus 1. There are two partial fractions. There are two fractions that we get for this. A over u minus 2 plus b over u minus 1. Multiply this on the other side. That gives you 2u equal to or identical to a into u plus b into u minus 2. Input some values of u now. We can input u equals 1. That makes the first bracket 0. U equals 2. That makes the second bracket 0. So once what you do is you input u equals 2, and then you input once you input u equals 1, and then you input u equals 2. Let's see what we get from that. Let's input u equals 1. That gives us 2 into 1 equals 0 plus b into 1 minus 2. And minus b equals 2, b equals minus 2 from this. Then you input u equal to 2. And that gives us u equals 2 gives us 2 into side. On the right side, we have a times minus 1 plus 0, and the value of a turns out to be 4. So a is 4 and b is minus 2. So what's the integral going to become? Now the integration becomes, if we write down the partial fractions, first of all, the partial fractions are 2u over u minus 2 into u minus 1. That simplifies to 4 over u minus 2 and minus 2 over u minus 1. These are the partial fractions that we get from this. Now what we do is we integrate each one of them separately. This is the integration that we wanted to do. Let's try that. Integration of 2u over u squared minus 3u plus 2. We had to integrate this with limits 3 to 5. Okay, now we have converted it to this form. We've broken it down into two fractions, 4 over u minus 2 with respect to u. This is du here. Minus integration of 2 over u minus 1 with respect to u. How do we integrate this? We can use the ln rule. The derivative of u minus 2 is 1, so we want 1 in the numerator. I can write 4 outside for that. Derivative of u here is also 1. I can write 2 outside. That leaves me with 1 over u minus 1 inside. So the integration becomes 4 into ln of u minus 2 minus 2 into ln of u minus 1. Now you input the limits. Limits are from 3 to 5. You input 5 in this one, then you input 3 in this, and then you simplify that. Input 5, and that gives you 4 into ln of 5 minus 2 minus 2 into ln of 5 minus 1. Subtract from this the case when you input 3, and that gives you 4 ln of 3 minus 2 minus 2 ln of 3 minus 1. Let's simplify this. We get 4 ln 3 minus 2 ln 4 minus 4 ln 1 plus 2 ln 2. ln 1 becomes 0, and we're just left with 4 ln 3 minus 2 ln 4 plus 2 ln 2. What did we have to show? We had to show that it is ln a, where a is a rational number in simplest form. We want one single log term that we generally want at the final result. Anyway, this becomes 0. If you want to make it one single log term, we can take these numbers to the powers first of all. So it becomes ln of 3 raised to power 4 minus ln of 4 squared plus ln of 2 squared. So that basically gives us ln of 81 minus ln of 16 plus ln of 4. We can use division and multiplication laws now to write this as ln of 81, whichever terms are positive, they are going to be in the numerator. 81 is going to be in the numerator. This 4 is going to be in the numerator. They're going to get multiplied. The term that has minus with it, that goes to the denominator using division law, and we get 16 in the denominator, and that simplifies to ln of 81 over 4. And that's what you wanted. That's our final result. They wanted a rational number in its simplest form. 81 over 4, it cannot be simplified further, and that's our final answer. That's what you have to write there. Okay, is that all right? That's the first part. Let's move on to the next one. Now it says find the area of the exact region R. Now for finding that area, we also need the limits. We only have the lower limit, that is 0, but we do not have the upper limit. We do not have the upper limit that's given. Okay. We cannot assume that it's pi over 2, although it looks like from what they're saying here that m is between pi over 2 and 3 pi over 4. we should confirm that by checking out the answer for this equation when we put y equal to 0. So let's put y equal to 0 and see what that gives us. 0 equals sine of 2x into 1 plus sine of 2x. That means either sine 2x is equal to 0 or 1 plus sine 2x is equal to 0. What does the first one give you? When is sine 0? Sine is 0 at 0, and then at pi, and then at 2 pi, and so on. So 2x could either be equal to 0. Okay, that's one possibility. 2x could either be equal to pi, and so on. So we're getting x equal to 0. That's one x-intercept. That's this one. That's not what we need. Do we have another one? From the next one, we get x equals pi over 2. Okay, that's the next x-intercept that we're getting. And that's turning out to be pi over 2. Now, that could be this point. That could be this point. But let's just check from the other equation as well. What do we get from that? Sine 2x equals minus 1. Now, this is a negative value. Which quadrant is that going to be in? Second or third or fourth quadrant? We can find the basic angle for this if we want. Although, you can also just use the graph for this. Let's use the graph. Sine is minus 1 at this point. This is 3 pi over 2. So you can say 2x is equal to 3 pi over 2. What does that give us? That gives us x equals 3 pi over 4. That's the next x-intercept that you're getting. And that's 3 pi over 4 here. So what's the point that you're looking for then? Pi over 2. This is going to be the upper limit that you have. Is that okay? That's going to be the upper limit. Okay, now, once you have the upper limit, now what you have to do is you have to integrate this function. Integrate this function for limits from 0 to pi over 4, and you get the result from that. How do you integrate this now? That's the question. Integration of y, which is sine of 2x into 1 plus sine of 2x with respect to x, with limits from 0 to pi over 2, right? That's the formula for area. Integration of y with respect to x, and limits are from whatever values of x we have as the limits. They are the limits. In this case, the limits are from 0 to pi over 2. Okay, now, how do we integrate this? That's the question. It's a product now. Do we use the integration by parts formula for this? That's not going to help because we've got a trigonometric function outside. We've got a trigonometric function inside bracket. It's not going to simplify. That's going to make things complicated. What we can do is we can just simplify this first of all and see what that gives us. Let's do the simplification. And from that, we get sine of 2x plus sine square of 2x with respect to x. That's what you want to integrate now from 0 to pi over 2. Now, what's the integration of sine 2x? Integration of sine is just minus cos. So it becomes minus cos 2x divided by 2. So this integration is straightforward. We can do that like this. But the problem is, let's just keep it as it is for now. We can input the limits at the end. How do we integrate sine square of 2x? That's the question now. Integration of sine square 2x. Remember, for sine square, cos square, what we have to do, we have to use the double angle identity for cos. Okay, we've got to use the double angle identity for cos. You need to remember that. Otherwise, in the exam, you'll not be able to figure that out yourself. The even powers of sine and cos, they're always integrated using the double angle identity for cos. So what we can do is we can say the double angle identity for cos that has sine in it, that is 1 minus 2 sine square a. Okay, let's make sine square a the subject from this, and that gives us 2 sine square a. That's identical to 1 minus cos of a. And then sine square a, that is identical to 1 minus cos of a divided by 2. Now, in this function, we have 2x in place of a. So what is 2x going to be? What is sine squared 2x going to be identical to? If this angle is A, the angle on the right side, okay, sorry, I missed the 2A there. Sorry about that. This is cos of 2A. Just thinking why they both the same. This is 2A. Whatever is the angle on the left side, the angle on the right side, that is supposed to be, this was supposed to be the double angle identity, right? This is cos 2A. That's identical to 1 minus 2 sine square. Whatever is the angle on the left side here, on the right side, it has to be twice that. Okay? If we have 2x on the left side, on the right side, we would have 4 times it. So sine squared 2x can be written as 1 minus cos of double of 2x, which is 4x divided by 2. So I can replace this integral now, integration of sine squared 2x, with 1 minus cos of 4x divided by 2. And that's an integration that we can do directly now. Okay? Let's simplify this further. It gives us minus cos 2x over 2. We can write this 2 outside, and that becomes 1 over 2. What's the integration of 1 with respect to x? That's just x. Integration of cos of 4x with respect to x, that's going to be sine of 4x divided by 4. And now we've got the final integration. We can input the limits now. Let's do some simplification first. Minus cos 2x over 2 plus half x minus 1 over 8 into sine of 4x. Now let's input the limits. Limits are from 0 to pi over 2. Let's input those limits. Let's input pi over 4 first of all. So it becomes minus cos of 2 pi over 4 divided by 2 plus 1 over 2 into pi over 4 minus 1 over 8 into sine of 4 pi over 4. That's the sine of pi. Subtract from this the case when you input x equal to 0, and that will give you minus cos of 0 over 2 plus 1 over 2 times 0 minus 1 over 8 times sine of 0. Okay, now let's simplify this. Cos of pi over 2, you can evaluate this on your calculator if you don't remember that, but cos of pi over 2, that's 0, right? Just put that on your calculator. The first term is going to become 0. Then the next one, that's pi over 8 minus 1 over 8 into sine of pi. What's sine of pi? That's also 0. You can put that on your calculator, you get 0 for that. This also becomes 0. Cos of 0 is 1, so this becomes minus 1 over 2. We'll evaluate this on your calculator again. Plus 0. Sine 0 again, that's also 0. So we've got a lot of zeros here now. And we're left with pi over 8 minus 1 over 2. That becomes plus 1 over 2. And that's your final answer. That's the area of that area. That's the area of that shaded region that we were looking for. It turns out to be pi over 8 plus 1 over 2. And that's our final result. Is that okay? Are you sure? Sure. Let me check quickly. 0 to pi over 2. These were the limits, right? Okay, can you input can you check the working again quickly? Have I done any error in the calculation? Okay, sorry about that. I correct that. Nobody pointed that out as well, apart from one. Yeah, thank you for pointing that out. So the upper limit is pi over 2, and for some reason, I wrote pi over 4 here. Okay, so that was pi over 2. Okay, so this was pi over 2 and not pi over 4. So what I'll do is I'll correct that. This was pi over 2 here, right? It was pi over 2, but I by mistake wrote that as pi over 4. So if that's pi over 2, then these values are actually going to change. This becomes 2 pi over 2. And this is pi over 2. And this is 4 pi over 2. Okay. Now, cos of 0. Yeah, the second calculations are all correct because the lower limit was the same. So it becomes minus 1 over 2 plus 0 minus 0. Okay, what about this now? Minus cos of pi. Minus cos of pi is minus 1, so it becomes minus into minus 1 over 2 plus pi over 4 minus 1 over 8 into sine of 2 pi, that is 0. So this does become 0. Okay, so this is what I'm getting then. It becomes 1 over 2 plus pi over 4 plus 1 over 2, and that gives us pi over 4 plus 1. Yeah, okay, thank you. This is the final result that we get. That's pi over 4 plus 1. Okay, so the upper limit there was supposed to be pi over 2, not pi over 4. Is that okay now? Okay, so how would you check that in the exam? How would you check that in the exam? In the exam, you would just put this whole thing on your calculator to verify your answer. So you'll say this is sine of 2x into 1 plus sine of 2x. Put this whole thing on your calculator like this. Input the limits. Limits are from 0 to pi over 2. 0 to pi over 2. Let's input those limits. That's 1.785. That's what I'm getting, right? 1.785. Now the final result, you can see what that turns out to be. If that's equal to this, then that means this is correct. 1 plus pi over 4. And that's giving me the same result, 1.785. And that confirms that this answer is correct. So if you had done that mistake, earlier we were getting pi over 8 plus 1 over 2. When we input that wrong limit, you would realize that you've done some error and you would recheck your working and hopefully find that error that you did the first time. Okay, this is the next question that we're doing, question number 10. Given that 2x equals tan of y, show that dy over dx equals 2 over 1 plus 4x squared. Okay. So we need to show that dy over dx equals this. Now, how do we think about this? One idea is that we use implicit differentiation because y is not the subject. But the problem with that would be, if we use implicit differentiation here, we would end up getting something like this. If I differentiate both sides with respect to x, I would get 2 equal to derivative of tan, that is secant, so that will be secant square y, into dy over dx, right? And I'll end up getting something in terms of y. And then I'll have to change that to x somehow, and that might make things a bit more complicated. An easier way of doing this would be, because you see, when you do implicit differentiation, in your final result that you get something that is both in terms of x and y. So in this case, you end up getting 2 over secant square y, which is a valid dy over dx expression, but we want it in terms of x. Since we want the result in terms of x, it'll make things easier if we make y the subject in this case first. Generally, we don't do that when y is not the subject. We just use implicit differentiation. But in implicit differentiation, in the final result, we get something in terms of x and y both, right? We don't want any y here. So for that reason, you should first make y the subject in this case, and that will make things easier. How do you make that the subject? You take tan to the other side, and that will become y equals tan inverse of 2x. And now we know how to differentiate tan inverse of something. What's the derivative going to be? The rule is the derivative of tan inverse of x. That is 1 over 1 plus x squared. That's what the formula sheet says. So this would end up becoming 1 over 1 plus 2x whole squared. But then whatever x is replaced with here, you also have to multiply by the derivative of that. So you multiply by derivative of 2x, which is 2, and that gives you 2 over 1 plus 4x squared. And that's your final answer. Okay. If you do implicit differentiation, you can also do it that way, but it will make things much more complicated. You'll get something in terms of y, and then you'll have to convert that to something in terms of x yourselves. Okay. That's the first part. Any problem with this? Any problems? You'll have to use trigonometric identities there, yes. If you were to do it that way. Yeah, you can do it with using implicit, but you'll have to use trigonometry. It will take a couple of more steps. It's doable still, not that difficult. It should work. But this is, I think, quicker if you make y the subject here. Yes, Nabia, that's fine. That works. That's correct as well. That's correct. Okay, let's move on. 10b. Hence, find the exact value of x tan inverse of 2x. Now, it's a 7-mark question. It's a product, x into tan inverse of 2x. So we'll have to use integration by parts for this. Now it says hence, so we have to use the previous part somehow. In the previous part, what we have done is we have shown that derivative of tan inverse of 2x is this. Okay. Let's use integration by parts. Which one of these two expressions we take as u and which one do we take as v dash? Think of isolate. One is algebraic, that's A. The other is tan inverse, that's the inverse trigonometric. Whatever is on the left side in isolate, that's u. Whatever is on the right side in isolate, that's v dash. So we can say u is going to be the inverse trig function, which is tan inverse of 2x. And v dash is going to be x. Now, what's the formula? The formula is integration of uv dash, that is equal to uv minus integration of u dash. We just have to input values in this now. Find the derivative of u. We found that in the first part. Derivative of tan inverse of 2x. What's that? Derivative of tan inverse of 2x. That's 2 over 1 plus 4x squared. We can just use that directly. This is 2 over 1 plus 4x squared. What's v? Integration of x. That would be x squared over 2. All right. Just input values in the formula now. The formula says integration is going to be uv minus integration of vu dash. Let's do that. U as it is, that means tan inverse of 2x, tan inverse of 2x as it is, into v, which is x squared over 2, minus integration of vu dash, that means x squared over 2, times u dash, which is 2 over 1 plus 4x squared. Now we have to integrate this thing. We're getting x squared over 2. Forget about the limits for now. We will integrate everything and then we'll input limits at the very end. Okay. So we have x squared over 2 into tan inverse of 2x minus 2 and 2, they get cancelled. Integration of x squared divided by 1 plus 4x squared. And now the question is, how do we integrate this fraction? X squared over 1 plus 4x squared, how can we integrate this? Do any of the fraction rules work here? Any of the fraction rules, do they work here? ln rule, what's the derivative of the denominator? That's 8x. We have x squared in the numerator. ln rule does not work. Tan inverse, it looks like the tan inverse form in the denominator, but the numerator has to be a constant for that, so it's not that. Partial fractions, it doesn't work. Partial fraction does not work because the denominator cannot be factorized. It cannot be factorized. Why are so many people saying partial fractions? How will you do partial fractions here? Denominator cannot be factorized. There's no formula for this directly in the formula sheet. There's no formula for this directly in the formula sheet. There's none. It's not tan inverse form. It's not ln rule. It's not partial fractions because the denominator cannot be factorized. If it was 1 minus 4x squared, then yes, that would be factorized to 1 plus 2x into 1 minus 2x. A square minus b square is a plus b into a minus b, not a square plus b square. So it's not partial fractions. It's an improper fraction. X squared, it's an improper fraction. What do we do with improper fractions? We break them into quotient plus remainder over divisor. It's an improper fraction. So we do division. We do division for this. Let's do that division. X squared divided by 1 plus 4x squared. Let's write that in the proper order. Higher power first, 4x squared, then 0x plus 1. What do we multiply 4x squared by to get x squared? We multiply it by 1 over 4. So that's what you have in the new in the quotient there. 1 over 4 into this, that gives you x squared. Plus 1 into 1 over 4, that's 1 over 4. Or you can say 0x first, and then you have plus 1 over 4. Change the signs. This becomes negative, negative, negative. This gets cancelled. And we have minus 1 over 4 left at the end. This is the remainder. And we've got the quotient on top here. That's the quotient. So we break that fraction as quotient plus remainder over divisor. So let's simplify this now. X squared over 2 into tan inverse of 2x minus. Let's split it into two parts. Quotient plus remainder over divisor. Quotient plus remainder over divisor. How does that work? Quotient is 1 over 4. You integrate that separately. Plus remainder over divisor. What's the remainder? Remainder is minus 1 over 4 over the divisor, which is 1 plus 4x squared. You integrate this thing separately. Now, let's simplify that further. X squared over 2 into tan inverse of 2x minus 1 over 4x minus 1 over 4 into integration of 1 plus 4x squared. And now we integrate this. What rule do we apply here? We could use the tan inverse rule. Okay, I'll come to your questions in a moment. Let's complete this, and then I'll explore that possibility. So we would not actually call that partial fractions as such. So what I'm thinking of is, what you're suggesting is that we write the denominator as what? You just do this. That's not partial fractions. So you'll say, you're probably thinking of writing it as a plus b over 1 plus 4x squared, like this. Is that what you're saying? Did you do it like this? Like you wrote it in this form? Because there's no way that you can break the denominator here as such. Bx plus c in the numerator as, okay, yeah, so bx plus c in the numerator. But again, it's not partial fractions as such, because you're not, in partial fractions, you basically break the denominator. You break the denominator. Yes, but there's only one factor in the denominator, right? There's only one factor. But yes, it'll work like this. It'll work like this. But we don't call it partial fractions as such, because this is just division. Partial fraction would be if this denominator was broken into multiple parts. This is just another way of doing long division. It's just another way of doing long division. So this is also division. A is the quotient, this is the remainder, and this is the divisor. So that's quotient plus remainder over divisor. So we're essentially doing division here as well. Okay. So those of you are asking, that would be another way of doing this without long division. Yes, that'll work. That'll work. But that's also division. That's not partial fractions as such. But if you want to call it that, that's okay. That works in this case. But you will still need to know this long division method, because if instead of x squared here, you had x cubed, then that no longer works, right? You can't break it like that anymore, because this thing would no longer be a constant anymore. You would have to do division then. Okay, you would have to do division. In this case, since the power was the same in the numerator and in the denominator, you could do it like that. But you still need to know this method as well, because there will be cases where you will only be able to do this. Okay. All right, now let's integrate this further. This is the only integral that we're left with. How do we integrate this? What form is this? Constant in the numerator, in the denominator, we have one x squared term, one constant term. What form is that? That's tan inverse form. Yes. So we can write it in that form. So what I can do is I can do it in the same step. So we don't have to write all of that again. So we recognize that this is tan inverse form. For tan inverse form, the rule that's written in the formula sheet looks like this. 1 over x squared plus a squared, that integrates to 1 over a into tan inverse of x over a, right? So we want 1 in the numerator. We can write minus 1 over 4 outside. That will leave us with 1 inside. In the denominator, we want x squared plus a squared. We've got 4x squared here. I can take 4 common from the denominator as well, so that the coefficient of x squared becomes 1. Let's write 4 outside from the denominator as well. What does that leave us with? Take 4 common from 4x squared, that leaves us with x squared. Take 4 common from 1, that leaves us with 1 over 4. This is what it becomes. Let's simplify this further. X squared over 2 into tan inverse of 2x minus 1 over 4x plus 1 over 16 outside, right? 1 over 4, that becomes 1 over 16. Integration of 1 over x squared, we want a squared, right? So we can write 1 over 4 as 1 over 2 squared. And now we can integrate this. In place of a, in that rule, we have 1 over 2. So just apply this rule, input 1 over 2 in place of a here, and that will work. Okay, let's do that. So integration becomes x squared over 2 into tan inverse of 2x minus 1 over 4x plus 1 over 16 into 1 over a. A is 1 over 2. So 1 over 2 into tan inverse of x over a, which is x over 1 over 2. And that completes our integration. We can simplify this and put the limits down. Any problems until this point? Any problems until this point? It's all right, right? Let's simplify this before we input limits. X squared over 2 into tan inverse of 2x minus 1 over 4x plus. This 2 goes to the numerator. In fact, you can just do cancellation right now. We can have an 8 here. So it becomes 1 over 8 into tan inverse of this 2 goes to the numerator and becomes 2 times x. That's the integration that we're getting. Now these are the same terms, or let's just keep them as it is. This is what we're getting. Input limits now. Limits were 1 over 2 to under root 3 over 2. Let's input those limits. You have to show working. You want an exact answer at the end. That means we need to write down the steps. We need to show the steps. 1 over 2 to under root 3 over 2. Actually, yes, you're right about that. That actually makes this much quicker. In the first part, remember, we've recorded about the first part. In the first part, we proved this, that the derivative of tan inverse of 2x, in the first part, we proved that the derivative of tan inverse of 2x was 2 over 1 plus 4x squared. So we could actually use that result to do some of this working quicker and get to this result faster. So yes, you could actually skip a couple of these steps. you could use the result of the first part instead to make that quicker. Yes, that would have been slightly more efficient. You could reduce a couple of steps here. But okay, we've done it this way now. Let's just input limits. But you're right, we could do that. Under root 3 over 2 whole squared, you have to show the limits, the steps that in which you're inputting the limits, you have to show that. Under root 3 over 2 whole squared divided by 2 into tan inverse of 2 under root 3 over 2 minus 1 over 4 into under root 3 over 2 plus 1 over 8 into tan inverse of 2 under root 3 over 2. This is what you get when you input under root 3 over 2. Subtract from this the case when you input 1 over 2. So that will be 1 over 2 whole squared over 2. You have to write all of this down. Tan inverse of 2x over 2, that becomes 2 over 2, minus 1 over 4 into x, which is 1 over 2, plus 1 over 8 into tan inverse of 2x, which is 2 into 1 over 2, that's 2 over 2. Now we simplify this. Now you can do step by step on your calculator. What does this result in? What does this result in? Under root 3 divided by 2 squared whole divided by 2. We get 3 over 8 outside times tan inverse of under root 3. Tan inverse of under root 3, what's that? That's going to give you pi over 3. You can put this on your calculator, you get pi over 3 for that. Minus 1 over 8 under root 3 plus 1 over 8 into tan inverse of under root 3. That will also give you pi over 3. That's what you get when you input x equal to under root 3 over 2. Subtract from this the case when you have 1 over 2 here. 1 over 4 over 2, that will be 1 over 8. Tan inverse of 1, that is pi over 4. Minus 1 over 4 into 1 over 2, that's minus 1 over 8. Plus 1 over 8 times pi over 4. And now you simplify this, it becomes pi over 8. Or you can say 1 over 8 times pi minus 1 over 8 times square root of 3 plus 1 over 24 times pi minus 1 over 32 times pi plus 1 over 8 minus 1 over 32 times pi. Now you can input this on your calculator, input the pi terms and see what they give you. You want an exact answer at the end, remember. Let's see what the pi terms simplify to. 1 over 8 and then plus 1 over 24 minus 1 over 32. Can somebody please confirm these calculations as well? The pi terms, they give me 13 over 96. Is that what you're getting? 1 over 8, 1 over 24, minus 1 over 32. There was another minus 1 over 32. That was hiding behind the calculator. So it becomes 2 over 32. That's 5 over 48, right? Okay, 5 over 48 times pi. Okay, now the under root 3 terms, there is only one of them. That's minus 1 over 8 under root 3 and plus 1 over 8. That's the exact answer that we're getting. Okay, now at the end, yes, if you have time, what you should do is check this on your calculator and you can do that. You can confirm this answer on your calculator. How do you do that? You would input this whole thing, making sure your calculator is in radian mode. Integration of x into tan inverse of 2x. Limits are from 1 over 2 to under root 3 divided by 2. Input this on your calculator. Your calculator is giving you 0.23574. Okay, your calculator cannot give you exact values. Now, what you do is you input this thing on your calculator. What you are getting, 5 over 48 times pi minus 1 over 8 times under root 3 plus 1 over 8, and see what that gives you. This is also giving you the same result. That means this is correct. Okay, if it's not correct, that means you might need to check your working again for any careless errors that you might have done. Next, we've got question number 11. That's the last question for today, and that's substitution. A lot of people have asked about this. Let's try this now. Use the substitution 2x equals tan of theta to find the exact value of this integral, and that's just one single part of 9 marks. Okay, how do we do this? 12 over 1 plus 4x squared whole squared dx. Limits are from 0 to 1 over 2. The substitution that we have to use is 2x equals tan of theta. That's the substitution that we need to use. Now, first of all, what we do is we differentiate this substitution so that we find, so that we can replace dx with d theta as well. So what I can do is I can say x is equal to 1 over 2 tan theta. And then what about dx over d theta? What does that turn out to be? That would be 1 over 2 as it is into secant square theta. Right? Derivative of tan is secant square. And now we make dx the subject because we want to eliminate dx from here. So we make dx the subject for that. And that gives us dx equal to 1 over 2 into secant square theta into d theta. And now we have to input these two substitutions, this and this. Okay, now how do we do that? Let's input values here. First of all, I can write 4x squared as 2x whole squared. So I can use that substitution then. 1 plus 2x whole squared, right? 4x squared can be written like this. And then there's a whole square on top of that as well. We have dx outside. Let's put that substitution now. I'm going to replace 2x with tan theta. So it becomes 1 plus tan square theta whole squared in the denominator. Replace dx with this thing. So it becomes 1 over 2 into secant square theta d theta. This is the integral that we're getting from this. Okay, we have done the substitution. We can change the limits as well now. Don't forget to do that. Okay, limits for values of x. We will clearly write what the upper limit is and what the lower limit is because sometimes they end up getting switched. Okay, what's the upper limit? Upper limit is x equals 1 over 2 and the lower limit is x equal to 0. Let's use that substitution. Tan theta is equal to 2 times x. So we can say tan of theta is equal to 2 into 1 over 2. Tan theta equals 1. The value of theta will turn out to be pi over 4 from this. Here we say tan theta is equal to 2 times x. That means 0. That gives us theta equal to 0. So the lower limit is 0. And the upper limit is pi over 4. That's what we input here. Okay. Lower limit is 0 and the upper limit is pi over 4. Now, how do we integrate this? Let's try to simplify this and see what that gives us. 1 plus tan square theta is what we have in the denominator. We know that 1 plus tan square theta, that simplifies to secant square theta, right? That's an identity that we've got. 1 plus tan squared theta is identical to secant square theta. So let's replace it with that. In the denominator, we can say that this becomes 12, or we can do some cancellation first. This gets cancelled with this, and we're left with just 6 here. So that ends up giving us 6 over secant square theta whole squared integration of this from 0 to pi over 4. And we have secant square theta into d theta here. What does that give us? Secant square theta whole square. So one power of this gets cancelled with the secant square theta, and we're just left with 6 over secant square theta d theta. That is what we have to integrate now. How do we integrate this now? 6 over secant square theta. Can we integrate this directly? If it was in the numerator, we could integrate this directly because integration of secant square is just tan. But this is in the denominator. We would have to apply some other rule. This does not work. None of the fraction rules work. None of the fraction rules work. You cannot do, you cannot use ln rule, tan inverse, partial fractions, improper fraction. None of them works. Let's take secant square to the numerator. What does that become? It becomes cos square. If you take it to the numerator, it becomes 6 into cos square theta d theta. Now, how do we integrate cos square theta? Now, first of all, what should we not do? Let me tell you about that first. Cos theta whole squared, you cannot use power rule here. You can't say cos theta whole cube divided by 3 and then the derivative of cos is minus sine theta divided by that. That's wrong. You cannot do it like that. Power rule does not work here because this is not a linear function. Cos theta is a curve, right? You cannot use power rule in this. This does not work. Okay. So what does work in this then? Cos square theta, power of cos. You need to know how to integrate powers of cos. Even powers of cos, power 2 and power 4, they are integrated using trigonometry. You need to remember that, right? You should have done that. Integration of cos square, we study that as a separate method. Integration, how do we do that? Cos square, how do we integrate this? Integration of cos square. We do this using trigonometric identities. What identity? The double angle identity for cos in particular. Cos 2 theta can be written as 2 cos square theta minus 1. If we rearrange that, that gives us 2 cos square theta. That's identical to 1 plus cos 2 theta. And then that becomes cos square theta identical to 1 over 2, or you can say 1 plus cos 2 theta divided by 2. So we can replace cos square theta with this thing because we have to get rid of this power. We cannot integrate with this power because the power rule does not work here, right? Power rule only works when the expression inside is linear. This expression is not linear, so that does not work. So what we can do is we can replace cos square theta with that thing now. 6 into 1 plus cos of 2 theta divided by 2. Okay. 2 and 6 get cancelled. That gives us 3. And we've got 0 to pi over 4 outside as the limits. How do we integrate this now? We can keep 3 as it is. That remains as it is, right? That's a constant that's multiplying. Nothing changes to that. Nothing changes in that. Integration of 1 with respect to theta, that's just theta. Integration of cos 2 theta with respect to theta, that's going to be sine 2 theta divided by 2. And that's your integration done. You can input the limits now. Limits are from 0 to pi over 4. You can keep 3 outside if you want. That also works. You can keep it inside. It's your choice, however you want to do it. Now you just have to input the limits from 0 to pi over 4. Okay. What I'm going to do is I'm just going to simplify this first of all. So it becomes 3 theta plus 3 over 2 into sine of 2 theta. And now input the limits from 0 to pi over 4. Let's input those limits now. So first of all, we input pi over 4 as the limit. 3 into pi over 4 plus 3 over 2 into sine of 2 pi over 4. Subtract from this the case when you input theta equal to 0, and that will make everything 0 because 3 times theta is a 0 and sine 0 is also 0. So this gets eliminated and we're left with this 3 pi over 4 plus 3 over 2 into sine of pi over 2. Sine pi over 2 I think is 1, right? Yeah, sine pi over 2 is 1, so this becomes this. And that's your final answer. It's 3 pi over 4 plus 3 over 2. What did they want from us? a plus b over pi, a plus b pi, where a and b are rational numbers. So yeah, we have that. We can write the constant version if you want. 3 over 2 plus 3 over 4 times pi. That is the final result that we got. Is that all right? Any questions on this? No problems. And now you can confirm this. This was a big integral, right? 9 marks. You can just put this on your calculator to see if that's correct. Use the integration function. Use the integration function, making sure your calculator is in gradient mode, although in this case doesn't matter because we're just using x here. Integration of 12 divided by 1 plus 4x squared, and then you do whole square of that. Limits were from 0 to 1 over 2. That gives you 3.856. 3.856, and you're getting 3 over 2 plus 3 over 4 times pi. And that confirms your 9 mark question. That's correct, right? So that's the final answer. This is what we're getting.